Hello there. This is Andric Peter, and this is my assignment for RAS 545 Robotic System 1, and this is the assignment number 2. So, the task of this assignment is to prepare the forward and inverse kinematic solution for the two-bot magician light robotic arm, and then also test it with the actual robot, and then perform the workspace analysis. And this is my assignment, and I'm going to explain the MATLAB codes which I have done so far. So I am using homogeneous matrices over here, as you can see. This is H01 or 0H1. But since MATLAB naming conventions doesn't allow you to have numbers before variables, it's named H01. And there are five matrices like this. And then we are just multiplying them to get H05, which is named as T over here. And then we are simplifying T, and then we are just simplifying those equations to get the x, y, and z values. We can also get the r values, and will more about that. So this is the homogeneous matrices over here. As we can see, this is cos 01 and sine q1, all that stuff. And anyway, in the end, we can see this is the most interesting part. This is the whole homogeneous matrix. And MATLAB simplify function simplifies all those complex equations, this really large equations into something that is more digestible. So this is the px value, py, and pz, and this value is our r. Okay, and the value which we will get is usually in radians, but the outcome of it will actually give us r value. Okay, let's see. So the values that I have entered by default here is 90 degrees, 25 degrees, 20 degrees, and 0 for R. So as we can see in this matrix, this value, since this is cos over here, this is also cos over here, R cos or A cos value, inverse cos, as you might say, would give us the R value. Just inverse cos this value, and then you will get the R. So let's see the solution. It is 294 point 3 millimeters and 79.6 millimeters. I have used meters over here since meter is the most conventional way, or it is the standard unit of measurement in most parts, but the robot uses millimeters and it's fine. So as you can see, these are the values. This is the R value, the R rotation matrix. And then similarly, I have also performed inverse kinematics over here for the same values. And then you are going to get a good joint angle over here. These are all not the exact solutions, but if you just wrap them all to 360 or even 180, the solution would be the same. Sorry. So this is the robot, and then I plan to move this joints at 90 degrees, 25 degrees, 20 degrees, and 0, like we did in the simulation. And let's see if the forward kinematic solution is correct. Run him. And then, as you can see, it is 294.35 and 79.64, which is close enough for the value. Since the conventions and the encoder values are different, we will not always expect the same values all the time. But in this case, we are lucky. We kind of got the same values anyway. So this is the first part of the assignment, to do the forward and inverse kinematic solution. The second part of the assignment, there is another MATLAB code called test robot DH2. I know the naming convention seems a bit weird, but bear with me. So basically, we are constructing a rigid body tree over here, and then we are just applying joint limits to it. So instead of using the URDF, we are just constructing a robot from the ground. I'll just run the solution, and then we can say it for ourselves. And this is the robot over here. We can even rotate it, and then we can see it is the same as the Dugo, just a bit. So this is a matrix which rotates in the z direction over here, and you can see the robot rotates this way. The last end effector is a rigid tree, and this is the tree which rotates it, also rotates it in the z direction. So it's pretty. Now let me open up the inverse kinematics designer. I think the command is inverse kinematics designer. Yes. So I love our new session over here. Uh, the robot is actually in the workspace. Okay. Yeah, the robot is in the workspace. Sorry. Just close this, please. Constraint pose. You can see the same robot over here in the individual kinematics designer over here. The neat thing about this is that we can just do this configurations over here. If the robot has collisions enabled, and then we add collision bodies over here, we can check for collisions, and then we can also solve for it. This is a neat solution one by one. So yeah, so one of the things I like to do is go to add constraints and then add uh, points constraint where I would basically constrain the X and Y rotation, and then I would just set it as free the Z axis. We can just toy around with it and we can see like how the robot behaves, and it's a really good method to check for your with face. So, what is the next part of this assignment? Next part is the workspace analysis and also the manipulability index for the pronunciation. So the first one is the Yoshikawa index. Over here, we can see the manipulability of the robot. And basically, what it means is that how easily the robot can move from one position to the other. The red one means the areas where it has a low manipulability, and the blue one is where the robots can actually. As you can see over here, the blue areas are pretty much similar because we can also see that is the same 135 degrees plus and minus. That thing works, so that is something that we can keep in mind. And we can also make sure see that the robot actually works as it's intended, and also the workspace seems kind of obvious and right. You see, as the robot gets near the joint, of course, the dexterity of the robot's end effector is not going to be high, and then this thing clearly simulates the error. Same is for the inverse condition matrix, as you can see over here. And then also the Ashida index, which actually says that how much of the force of the robot would be transferred to the joint, those parts. So these red dots represent those forces. And these are the workspace analysis for all the motion components. The same thing as in the XY linear grid. A good way to visualize this more intuitively is by using voxelized representation. And this diagram basically tells us how the robot is going to behave. As you can see, during the end areas, the manipulability of the robot is high. And as we kind of come to the middle, the manipulability decreases. It is like a slice of a toast, if that would be a good description of this. As you can see, the torus analogy also keeps the robot's manipulability is very high in these directions, which suggests that the robot is going to work well in these areas, and it is not going to work so well in these areas. And the figure is true. If you have worked with a real Dupont, you know that's true. So these are the MATLAB's part of my video of my presentation. And then The other part involves testing this code with the real do-bot and then verifying the forward and reverse kinematics. So there are two files over here, do-bot kinematics or do-bot.py, and then forward kinematics fkik2.py, which I use to test it on the actual robot over here. And this, I have screenshots of the terminal, which I'm going to explain later in this video. So the do-bot kinematics.py is basically like a library. So similarly, there are these matrices over here, which we used in the MATLAB. And instead of using Python, we are just using the SymPy library to solve for these matrices. And then we are going to calculate the inverse kinematic solution over here. So the X, Y, Z, and R values are the ones that is going to be returned by the forward kinematics function over here. And then even the R value is going to be returned over here because of the R cosmos function, which I mentioned earlier in the video. Similarly, there are a number of inverse kinematics functions over here. The one which I found to work the best is inverse kinematics 4 over here. The first method used the SymPy library, and since SymPy was really slow, the I have actually switched to SciPy library, which is lightning fast and almost always gives the solution which is the closest. So SciPy works in this situation. So yeah, the px and py equations are over here. And since I couldn't use the SymPy equations over here because of the library clashes, because SymPy uses its own symbol network symbol library, and then SciPy relies on NumPy. So we can't just plug it in and then expect it to work. We also need to give an initial guess over here, and then we are going to get the all the four data values. I'll just run the function over here so we can see. So I'm going to use the same matrices that we used over here. It's 90, this is 25, 20, and 0. So let's see what comes. This is going to take a while. We can't just expect it to run quite fast because again, Python is simple like the SymPy library is quite slow and it's not as fast as MATLAB. And in my experience, I found MATLAB to give more accurate values all the time. So these are the matrices which it calculates. And now we can see over here the values. Let me zoom in a bit. Yeah. As you can see over here, these are the matrices, the final equation x, y, and z over here, if you will. As you can see here, print x, y, and z over here, and also print the rotation metrics over here. And now the positions, it's 294.34 millimeters and 79.64 millimeters, and the R is 90 over here. Let's check if these values are right indeed. So it's 294.35, close enough. It's 294.346, so it is basically 335 cent. The similarly, it is 79.64 and the R value is 90. This is correct. And similarly for the inverse kinematics, it's 90, 25, 20, and 0, which is correct because I gave here. What I gave here is minus 25. As you can see, the rotation convention for my solution takes the rotation in the other direction. If you were to test during the robots, when I showed you the robots rigid dream model earlier, it doesn't matter. It works. So this is the solution that I have arrived so far. And then yesterday I checked it in the lab, and this is for the terminal. This is the terminal images. So this is when I ran the forward kinematics test. So the forward calculated forward kinematic position was 240, 0, and 45. And this is what the bot gave. And then this is the inverse kinematics position that we calculated. And this is the joint angles which was obtained from the robot. These are applied for multiple joints as well. And as you can see, it is pretty accurate all the time because the forward kinematics position is always down right to the, at least the error is like from a millimeter to two hundredths of a millimeter. The main reason for the error in the Python code is because the number is frequently being converted from one format to another. So there is Py float 64 format, which is being converted to the float format, and then it also gets converted to Py float, and then there are some data losses during these conversions. And also the solvers are not very accurate. So similarly for the inverse kinematics. So I hope you enjoyed this video and the session was as informative as I can. Thank you.